going to be forthright and like I just don't want to talk about them today. I haven't finished grading them all. But then also they just weren't the greatest in this period, specifically in this period. Yes, there'll be recovery, but we will just talk about all of that tomorrow once I have finished grading everyone's. So we can all just kind of make sure we are doing what we need to this semester. Hey guys at home, I am going to just restart my computer. So like, don't leave the meeting, please. I'm going to restart my computer to see if that fixes me being kicked out over and over again. So hang tight for 5 minutes and we'll just awkwardly stare at each other here. All right, guys, let's try this again. Again, fingers crossed that Teams wants to cooperate. So this unit that we're talking about is Unit 6. It deals with what we call methods of integration. This entire unit, we're just going to be dealing with just more integrals. Like we're not really going to get into the applications yet. We're going to keep it with the same applications that we had previously, that the definite integral represents in that area. But really until we can start getting to like the meat of integrals, we just have to know how to find integrals. Did want to talk a little bit about this unit. Like it's officially only 3 topics, but like 2 of them are big topics. Like I have 3 days to cover integrating with natural log. And then after the quiz, I have 3 days of integrating with inverse trig. What makes these hard is like all the problems look slightly the same, but they can be integrated in wildly very different methods. What also makes them difficult for some students is you have to be really good with some prerequisite algebra that shows up in some of these problems. Some of the algebra that shows up with these problems comes from anything from just like basic, rewriting, distributing, FOILing, factoring, but also things like long division of polynomials, completing the square. So yeah, lots of just fun algebra stuff that you probably haven't seen since Algebra 2-ish maybe. The quiz for this unit is going to be on the 4th. I know some of you might see that and be worried, the county's deadline for like recovery is like before the next summative assessment or something like that. I'm just going to make all recovery for a previous unit due by the test, and that's really like the big one for me. Again, I'll talk more about the recovery tomorrow just to give me a chance to finish grading everyone else's. But today what we are going to be looking at is integrating quotients using the natural log. If you're following along in OneNote, some things I shared with you that will be helpful. Looking towards the front of the notes, I shared just the blank derivative rules. These are all the derivative rules I expect you to know. To be honest, if you're new to me this semester, there's probably someone here you don't know, and you need to figure them out as soon as possible, just to be honest. And I also gave you an integral one. We don't know all of these yet, but these will be all the integral rules you'll have to know eventually. We'll know them all by the end of this unit. But today we're going to be integrating quotients using natural log. So to just go ahead and start with it, I do want to remind us about some stuff that we did first semester and then how that can kind of connect to stuff this semester. And then really it's just going to be like example after example. But not only will I be working out examples, but we will be spending a lot of time just like discussing how we decide which formula or which method to use. That's really going to be the difficult part of this semester. So if you remember, and I have found out those of you who are new to me, this is actually new to you as well, unfortunately. But for those of you who have me, we know that the derivative of the natural log of x is what? 1 over x. Like we know that the derivative of the natural log of x is 1 over x, or basically 1 over what you see on the inside. So like doing some chain rule stuff, if I have this example, what is the derivative of the natural log of negative x? It's going to be 1 over what we see on the inside. Then we have the chain rule. Well, what's the derivative of the inside? The derivative of negative x is negative 1. Well, that's just going to simplify and also give you 1 over x. Which leads to kind of this like other thing where, well, if I say, well, what's the derivative of the natural log of the absolute value of x? Well, if the natural log of x was 1 over x, and the natural log of negative x was also 1 over x, what do you think the natural log of the absolute value of x is going to be? 1 over x. It doesn't matter whether x is positive, it's 1 over x. Why do I show you that? To kind of show you where this integration rule is going to come from. So the first integration rule we're going to add to like our memory is going to be the integral of 1 over x dx. And the integral of 1 over x dx is going to be the natural log of the absolute value of x plus c. That absolute value does need to be there unless for some reason, you know, like the inside of it is always going to be positive. Why we are going to use that rule as a natural log of x, to kind of remind you, I'm going to kind of go over here in this blank space. We wouldn't be able to use the power rule for that one, because if you tried to use the power rule, then you would have basically the integral of x to the negative first power, which is not bad algebra, like you can do that, but if you try to evaluate that, add 1 to the exponent, divide by the new exponent, you end up with 1 over 0. We know that 1 over 0 math is undefined, so we won't be using the power rule when that denominator is raised to the first power. When our denominator is raised to the first power, that's going to be our big clue that it's going to be a natural log integral. Also, from now on, since we've already learned U substitution is going to apply to every single rule that we will learn in forever and ever. So I'm going to write all the rules from now on in terms of U, just to remind you that U sub is a thing, and you'll probably have to do U sub for most problems. So like after you do U sub, and we'll be looking at plenty of examples, the integral of 1 over U is the natural log of the absolute value of U plus C. So before we get into a lot of crazy examples, on the next slide, I'm going to show us 6 problems. And we're just going to talk about like, hey, is this going to be a natural log problem? Is this going to be something else? And if it's something else, do we know how to do it yet? Or is it still something that we will need to learn? Again, there's going to be a lot of decision making in this unit where you have to kind of look at a problem, first figure out the method to use, and then do it correctly. And again, what makes it hard in this unit, most of the problems we do the entire unit is going to be integrating some quotient, some fraction, but they can have wildly different answers and methods depending on just slight changes in exponents or slight changes in other parts of that problem. So the 6 problems I want to go ahead and start off with are these, and I have to ln or not to ln. So looking at these, we'll just kind of go line by line and talk about like, hey, is this going to be a natural log problem, or is this going to be something we know how to do? This first one, clearly that's the rule, so I'm not going to waste your time asking whether that would be a natural log problem. we see the integral of 1 over x. This is x to the first power. A denominator raised to your first power, your big clue that's going to be a natural log problem. Don't rewrite it using the power rule. It won't work. And this one, again, that's just the rule, the natural log of the absolute value of x plus c. For whatever reason, once I showed students the natural log rule, students want to make like every denominator a natural log rule. So you do want to be careful. The one next to it is not going to be a natural log rule. What's our big clue that that one next to it is not going to be a natural log rule? X to the third power. So our denominator is not raised to the first power. We actually know how to do that one. What would you need to do in order to integrate that problem? X to the negative third. This one is, we can rewrite it and use the power rule. Add 1 to the exponent, divide by the new exponent, plus c. So we have like new stuff and then old stuff. Looking at the two underneath it, I have the integral of 1 over 3x dx. Talk about that one first. Natural log rule or something else? Natural log, what's our big clue that's a natural log problem? It's x to the first power in the denominator. An easier way to do this one, scroll up a little bit. So again, big clue, this is to the first power, so I know it's going to be a natural log. If you want to avoid use of, which I recommend for this one, I would rewrite it a really easy way. And when I see this problem, I see that this integral, 1 over 3x, is the same thing as 1/3 times 1 over x. We know with fractions, you just kind of multiply straight across. I'm kind of like pulling that 3 off of the x. I do that because now that 1/3 becomes a coefficient. So I have 1/3. What is the antiderivative of 1 over x? The natural log of the absolute value of x plus c. What about the one next to it? Natural log rule or something else? What's technically the exponent on that entire denominator? -1 right now. When it's in the denominator, we'll just say it is to the what power? First power. So again, even though it's not just one term, technically that entire denominator is 3 plus x, all of that's to the first power. When our denominator is raised to the first power, big clue that it's probably a natural log. I am going to kind of emphasize when I say probably. Always want to try something, so let's see if it works out. So with a natural log problem, we often set the entire denominator equal to u. So I see u prime is just going to be 1, so it's actually going to be a pretty easy u substitution to do. This can be the same thing as the integral of 1 over u. dx is du over u prime, but u prime is just 1, so I don't need to worry about it. And then that is 1 over u, that's just going to be using our rule. The integral of 1 over u is the natural log of the absolute value of u plus c, and then you want to plug u back into the problem. Any questions on those 4 before we do those last 2?
Why couldn't you just like bring both of them to the denominator and then have like 1/3 be separate from 1 over x, like with the plus sign?
Let me see if I understand what you're asking. So you're asking about the one we just did?
Yes.
And you're asking why we can't split this up into 2 fractions? Did I hear you right, or is that not what you asked?
Yeah, but now I'm realizing that's bad.
Yeah, well, I'm going to show it just so people see why it's bad. So making sure you don't do bad algebra, you can't split up a denominator like that. Because you know that when you're adding fractions, they have to have a common denominator. So yeah, that would be some bad algebra you want to do. Caroline?
Would you have to like show, because like would you have to show like a u and then u?
I would probably not show you so.
Okay.
I would expect most students to jump from this to the answer.
Okay, I was just wondering.
Yeah, even if there's just like a coefficient, most of you can probably jump from the question to the answer pretty easily. Enrique?
So why did you do like? How did you go from u sub to doing the natural log?
So I did the u. Whenever you're doing u sub with natural log, we're going to let u be the entire denominator. So then u prime is 1, so like du over 1, nothing really to cancel out. And then this is just a rule. The integral of 1 over u is just the natural log of u plus d. Using this rule right here. What I have boxed in red.
Oh,
All right, let's go ahead and look at these last two. First one you see, and again, you can kind of see just by slight changes, I can make it a completely different problem. All these really have like x's and 3's in them for the most part. So this one I have the integral of 1 over the quantity 3 plus x squared. Natural log rule or something else? Something else, what's the big clue that something else is squared? So natural log rule is only going to be used when the denominator raised to the first power. This is one that we actually know how to do because we can just pull that up out of the denominator. Technically, u sub is happening. Don't really need to show it because if u is that 3 plus x, u prime would be 1. So there's like nothing to cancel or anything. I was getting ahead of myself and putting du there already. So you're really just integrating u to the negative 2. So then like finishing it out, add 1 to the exponent, divide by the new exponent, plug in u, and then don't forget about the plus c. What about this last one? Does it appear to be natural log rule or something else? It looks like natural log. What makes it look like it could be natural log? It's 1, so there's 2 terms, but what's the entire denominator technically raised to? First. So it could be natural log. And typically when the denominator is raised to the first power, it is natural log. But when we start trying this one out, so if u is equal to that 3 plus x squared, again, natural log will let the denominator be u. U prime becomes 2x. What's wrong with that u prime that we have? There's no x's. Nothing cancels out. There's just a 1 up there. So like that just doesn't work. I'll give you the answer to this. We're not going to talk about it because it will probably scare you. But the answer to this looks like this. And now you get to be excited for what's coming up in this unit. So like we're going to see that just by changing certain parts of the problem, like we can make it like a natural log problem, I can just slightly change an exponent and it becomes like a rewriting one, or I can change where the exponent's located at and it could be like an inverse squared problem. So like we can take problems, you can kind of argue all these look pretty similar, and we just have to kind of think about how we integrate them. And you can kind of expect things like this on the quiz and the test, where I have a page of just a bunch of integrals that look the same, but have wildly different answers based off of how things are arranged. So how does my brain work when I'm doing these problems? Scary thought getting inside my brain, but this is kind of what my brain does as I'm doing these problems. I find some students like the flow chart just messes them up, and I can't find a good way to kind of show how my brain works, but this is kind of what's going on. If you want to write this down, you can, but I will say I have a fully typed in version of it at the bottom of the notes. So like, don't really need to write this down because again, I find that some students it helps them, but for some it really does just like add to just the stress of it. So as we do problems, like I'm going to talk about like the decisions I'm making. Again, I know I have a lot more experience, but I'll kind of talk about like when I see a problem, this is what's happening in my head, so you can kind of be thinking about the same things. The first thing I always look for though is I will always look to see if the denominator is a monomial. So like if you just want to think of anything, if your denominator is a monomial, you're going to smile because that's going to be the easiest type of problem I can give you. So when your denominator is a monomial, why is it easy? Is you just want to divide everything by that denominator, simplify it, and then integrate. It's going to be the easiest problems we have when you're integrating quotients. An example of that would be something like this. Make that a little bit bigger. This would look at this one. I look at it. This looks like a complicated integral. Like you definitely have this long polynomial divided by 2x. But when I see this problem, I get happy because that's just a 2x. We have a monomial, so I know that I can easily simplify this problem, and then hopefully it will be something that I can do much more quickly. Easiest way to simplify when you're dividing by a monomial is just to divide everything in the numerator by that monomial. So I'm going to have the integral, I'll have 2x cubed over 2x minus 3x squared over 2x plus 8x over 2x minus 1 over 2x, and then don't forget my dx. Then I just want to simplify it. So then I'm going to have the integral of x squared minus 3/2 of x plus 4 minus 1 over 2x dx. And then from there, that looks very much like a problem you could have done on your test yesterday, except for that very last term, which we'll use our removal. So then that first term, we have 1/3 x cubed. 3/2 is a coefficient, but x squared, divide by the new exponent. 4 turns to 4x minus, this last one is where that new formula is going to come into play. Again, in my head, I think of this as 1/2 times 1 over x. X is raised to the first power. I know it's going to be a natural log rule. So that's going to become 1/2 the natural log. Don't forget the absolute value. And then, of course, also don't forget your plus c. So again, easy problems. See a monomial, divide everything by that monomial, and then just go from there. Questions so far? All right. Yeah, go ahead. Sorry, Mitch.
Yeah, so you kind of like broke it apart, right? So you put the.
Yeah, I pretty much like took it and then took it term by term. So instead of having like what was a quotient, it's now just a bunch of separate terms.
How is this example different from the one before where you couldn't break it up?
The one before, you didn't have a monomial. So again, like, I'm not going to write all big, but if you had something like 2x over like x plus 3, that can't be broken up. You can only break it up when you have a monomial. Like,
Oh, okay.
you can't, there's nothing to do to that.
So if it's the numerator has all that, then you can break that up, right?
Yeah.
Okay, cool.
So that's going to be the easiest one. Again, you're going to smile when there's a monomial. I would argue, though, one that's also going to be kind of easy to do. Like, let's kind of expand on Mitchell's question. Like, what happens when that denominator is not monomial? So again, I say in this unit, I can just change like slight things in the problem. So like, here's the problem we just did. It was divided by 2x. Now the one that I want to do is divided by 2x minus 3. Just by adding that minus 3 there, I've actually increased the difficulty of this problem, not significantly, but there's going to be a lot more work to do. But I would argue there's going to be something else we can do to help us integrate it. And it kind of explain what's going on. When I see this quotient, like it's some polynomials, it looks gross. Like just think of this though as like a fraction. Like fractions are our friends, like 1/3, 4/5, like we can think about fractions, right? I know this doesn't look like a simple fraction, but when I see that fraction to me is a top-heavy fraction. The degree of the denominator, and again, when I say degree, I'm talking about the largest exponent that I see. The degree of the denominator is less than the degree of the numerator. The degree of the numerator is a 3. The degree of the denominator is a 1. In many ways, you can think of this as a top-heavy function. That's kind of like the non-math way of saying it. So this is like a top-heavy function. It's like having a mix of number like 11/2 or 9/3 or something. We just want to find a way to simplify it to make it a little bit easier to deal with. Now we can't just divide everything by 2x minus 3. That makes it a little bit more complicated. We can't split it up that way. But we can simplify it, and we are going to simplify it by dividing. When we see a problem like this where it's top-heavy, we want to be able to rewrite this problem by simplifying it. And to simplify it, we are going to use long division. Which, when it comes to long division, not to throw shade at any other like previous teachers, but I feel like students see long division and they just want to be like, oh, it's so hard. And then like I show them like long division and they're like, oh, why was that so hard for me 2 years ago? Like it's not a difficult process. So like setting it up, to kind of teach it like an elementary school teacher, you have like, your house. I think that's what they call it maybe. The top one goes inside the house. That's what we're dividing. So I have 2x cubed minus 3x squared plus 8x minus 1. And we're dividing it by 2x minus 3. Again, don't lose sight of the ultimate goal. We're doing long division to simplify the original problem. So let's do my long division. I'll do green first. No, let's do a darker one. Red. 2x times what is going to give you 2x cubed? X squared. So I'm going to line it up. And then remember, you're going to multiply going around. So I have x squared times 2x, which is 2x cubed, x squared times -3, -3x. Subtract. Hopefully some columns cancel out. In this one, we're kind of lucky how 2 of them cancel out after subtracting. And then bring down what you have remaining. So you're going to have an 8x and a -1. And then you just want to repeat that process. 2x goes into 8x. So you think 2x times what is going to give you 8x? 2x times 4, positive 4. Multiply around. 4 times 2x is 8x. 4 times -3 is -12. Subtract. The 8x's cancel. -1 minus -12. That's the same thing as -1 plus 12, which is going to give you 11. 2x times what gives you 11? Doesn't work. That would be your remainder. See, not bad. Yes, Caroline?
Okay, oh, wait, never mind, I got it.
You good?
Yeah.
So that's just the algebra. Like, we haven't done any of the calculus yet, but we did that, so now that the calculus can be easier. So basically, when we have this original polynomial divided by 2x cubed, after dividing, it goes into it x squared plus 4 evenly, but then we have a remainder, so plus, what was our remainder? Our remainder was an 11, and that 11 could not be divided by the 2x minus 1. So to kind of highlight and see where things are coming from. There you go. And then, similar to that other one, where we just kind of integrated it term by term, we just want to integrate it term by term. Still want to be careful with u sub. These first two terms are pretty easy. So the integral of x squared would be 1/3 x cubed. The integral of 4 would be 4x. This last one, it's a quotient. What rule are we going to use to integrate that last one? Natural log, yeah. How do I know it's natural log? Raise to the first power. So u would be 2x minus 3. U prime would be equal to 2. So doing my u sub, this would be the integral. We have an 11 over u. Dx is du over u prime. Many of you could probably integrate it like that. I'm going to kind of pull out my coefficients. We're really just integrating 11 over 2 on the integral of 1 over u du. So I have my coefficient, the natural log of the absolute value of u, plus c. Again, many of you could probably skip all that stuff, the u sub. Like, I think many of you can see that u prime would be 2, and then the coefficient would be 11 over 2. In fact, I hope many of you could, but again, no shame in kind of showing work and seeing where that came from. So again, that's how we're going to use long division. Again, that algebra skill unit, I think you would see again, to kind of simplify this rational expression so that can become something that we can integrate. Questions or concerns you want to ask about that one? All right, so let's go ahead and kind of just keep talking about like what's going on in my head when I see quotients and I'm integrating. Anyone still writing that down though before I change it? All right. So again, in my head, things I am thinking about. I first always ask myself if I have a monomial. If I have a monomial, it's really easy. Just divide everything by that monomial and simplify it. If I don't have a monomial, I'm like, well, at least are they polynomials? Is there something that's just like, there's like no trig, there's no like weird square roots, like is it just a polynomial? If we're lucky and it's a polynomial, I kind of start comparing the degrees that we have. And again, if it ends up being like a top-heavy function, then I'm going to end up doing long division. I have on there clever splitting up, which I will show you. It's not my favorite method. It's just, well, you have to be clever to do it, and long division kind of always works, so there's kind of like less guessing and checking. But that's kind of what's going on in my brain. So looking at some other examples, 306, we'll do just a few more for today. Sometimes we look at a problem, we're like, well, it's not really top-heavy, but we're also not really dividing it by a monomial. So if I'm looking at this one, I have like the integral of this 6x plus 5 over 3x plus 2. So let's go ahead and deep dive into my brain what I see when I see this problem. When I see this problem, I look at the denominator, and I see that the exponent on the denominator is first. This is 3x plus 2, all of that's raised to the first power. So I know, like there might be some steps in between, I know eventually there's going to be some natural log that shows up somewhere. I don't have a monomial, so I can't just easily split it up into separate terms that way. Not obviously top-heavy, like the exponents are the same. So like one trick to do this one is like, let's just see if we can simplify it. Well, how will we simplify this one? We can still use long division and try it. And that's often what you will do when you see equal degrees. Like a good thing just to try to do is long division. That may not be the only thing that works. Like there is actually another way you can do that problem, but long division is probably going to be the best choice. So again, to kind of get you started on it, I'm going to let you finish it. I have this 6x plus 5, and I am dividing it by 3x plus 2. This one is thankfully a lot shorter long division than that other one. Marcus, you had a question?
Yeah, could you not split it up into like 6x plus 5 times 1 over 3x plus 2? Or would that be like 2?
So like, there will be ways to rewrite it, but that way wouldn't work, if I'm hearing you correctly. So doing a long division, you're like 3x times what is 6x? Just a 2. Multiply going around, 2 times 3x, 2 times 2. Subtract, just going to give you 1. 3x can't go into 1, so definitely a lot shorter long division than that previous one we did. How is that long division useful? It lets us rewrite the problem. So 6x plus 5 divided by 3x plus 2 is going to be equal to 2 and a remainder. The remainder was 1, and it was unable to be divided by 3x plus 2. And then you just want to find the antiderivative of each part. The antiderivative of 2 is just 2x. 1 over 3x plus 2. Here's where the natural logarithm shows up. That's all raised to the first power. U would be that 3x plus 2. U prime would just be 3. So now I have a coefficient of 1/3 in front. The natural log of the absolute value of u plus c. That is how I honestly would work out that problem. I am going to show you the other method. Again, I don't think many students will use the other method, but I just want to kind of show you that it is an option that works when you do have equal degrees. But questions on this one, Mitchell, go ahead.
So how do you know what's like inside, like the dividend and all that?
So the top part always goes, what's in the top of your fraction is always going to go inside, and what's in the bottom of the fraction always goes on the outside.
So like if you wanted to say 6x plus 5 divided by, that means 6x 5 in the middle?
Yes, because we're doing 6x plus 5 divided by the 3x plus 2.
Okay, all right.
So that's the way I would do that problem. This is another way to do it. Don't really have a name for it, but I do just want to kind of talk about, because sometimes students like stumble across this method just by accident when they're just like, I don't know, you've all been there. You're trying to like do some problem in your test and you're just trying to do like every possible thing, trying to get an answer. We've all been there. You can kind of like force this to work out other ways doing it without long division. And so another way to do this is you see this problem, you're like, okay, I know it's natural log. This is a denominator. It's raised to the first power. Let's just see what would happen if I wanted you to be my denominator, because that's what you would have to do if it was a natural log problem. U prime would be 3, but if we're looking at this, U prime is 3 and we have this whole like 6x plus 5 up top, and you're like, that's not going to work. So again, you kind of look at this and you're like, man, I really wish I could simplify this. And you kind of think to yourself, like, this is where you have to kind of be a little bit clever with it. You're like, man, I wish this numerator could easily simplify with that denominator. So think to yourself, what would that numerator need to be in order to like have it simplify with 3x plus 2? I'm not sure if I'm asking that the best way. I think another way I could ask it is, what would that numerator need to be if I wanted to eventually cancel with that 3x plus 2? Make it even easier than that. 6x plus 4. So Matthew says 6x plus 4. Again, why would 6x plus 4 be nice? If it was this, so again, this is like a big if. If it was 6x plus 4, you could factor out a 3, and it would be 2x. Try again, not factor out a 3. If it was 6x plus 4, you could factor out 2, and it becomes 3x plus 2, which would be nice because it could cancel. Well, in math, you can kind of make anything look any way you want it, as long as you don't change the problem. So like if I want it to be 6x plus 4, it was 6x plus 5, so I can be like, well, I'm just going to write it as 6x plus 4 plus 1 instead. That's the same thing. So then you can still factor out 2 from the first two terms, but then Mr. plus 1 is still hanging out on the end. So you can kind of force this to happen. Again, those are the same statements. Like if you distribute that 2 across, add the 1, you would get 6x plus 5. And then this is where you can kind of divide everything by that denominator. So normally we only divide by the denominator when it's a monomial. But as long as you split it up and have both parts divided by it, it would work out. So there's the first part. Plus, here's the second part. And then you're like, our goal was met. Those cancel out, and we're just left with a 2. What's the integral of 2 to x? That second part with the 1, natural log rule. And it would be 1/3 natural log of the absolute value of 3x plus 2 plus c. Which is the same answer we got with long division. But again, I would argue like some students just like see this, like their brains just look at it and they see it. Me, I love a good process, so I'm going to do long division because it works for me and it will always work. It never fails. But that is another way you could have done that problem. Yeah, Taylor.
Will the coefficient in front of the natural log, will it always be the numerator over the
I don't want to say that's always true. That will always be true if only your denominator is like a linear problem. Like 3x plus 2, 4x minus 1. Like if there start being more exponents here, I think then no, that won't be true. But for something this simple, yes, that will pretty much be the case. Let's do 315. Let's do one more example and then I'll stop for today. I'm gonna jump around. Yeah, let's try this one. So again, when we are looking at problems, again, you want to be able to just kind of reason your way through problems and like think through how you would do them. We've talked about rewriting the problem. We've looked at natural log. We saw problems that we rewrote that became natural log. So like here's another one. I kind of wrote up here already, like this is a case where the degree of the denominator is bigger than the degree of the numerator. So this one is not a top-heavy problem. So we wouldn't do long division. So I would just kind of open it up, and this is what we'll kind of wrap up today. what method would you want to try to do for this one? Any ideas? Because there's several ways, several things you can do. I can kind of think of two routes. You could do that, will both give you the right answer. Any ideas of what you might try to do on this one?
Synthetic division.
So synthetic division is just another way of long division. This one we won't be doing synthetic division because we don't have like a simple divisor like just x plus 3. So any other ideas what you could do, Caroline?
I was just gonna say, could you like simplify them though?
You could simplify it. So if I'm looking at this one, like all those terms have like a bunch of stuff in them. So like, let's just try simplifying it. In that numerator, what do they have in common? They just have an x in common, and we have this x plus 4. In that denominator, they have an x squared in common, and we have this x plus 6. Simplifying it, that's going to give me x plus 4 over x times x plus 6. Okay, we did that, now what?
Could you split it up?
How would you split it up?
1 over x times x plus 4 versus, or 1 over x plus x.
So you still have a bunch of products there. So like we want to kind of avoid the products if we're integrating.
Can you distribute on the ball?
Sure, we can put that x back in. Let's see if that will get us anywhere. And I'm saying it this way because like for a lot of these problems, like you just want to like try something. Like nothing hurts to just try something and see if it works out. So we put that x back across. Anything you see that you could possibly do now? Any ideas? So if you get stuck, what can you go back and do? Everyone's favorite, let's just go back to the beginning. Like, I don't know, that might work. I don't, we're stuck, whatever. Let's try something else. That way would work. There's some other things we need to do to kind of make that work. So let's kind of go back to the drawing board. And again, I'm not erasing that. Like, I want you to see the process of like, hey, sometimes we do stuff that just doesn't work out. So we want to try like a different method. Another thing, okay, so we saw simplifying wasn't the best thing to do. So I might look at this problem and be like, okay, you can't do long division. You don't have a monomial. Technically, what is that denominator raised to what power? The first power. So technically, all this is the first power. If our denominator is raised to the first power, what rule might we be able to use? Natural log. Let's try it. U sub with natural log. So I have u would be equal to the denominator, if this truly would be a natural log problem. So then u prime, that's going to give me 3x squared plus 12x. That's a really ugly u prime. But how is that related to what's already in the problem? It's a constant multiple of it. So if u sub is going to work, I can go ahead and factor out a 3 to kind of make it a little bit more obvious. So like we did eventually factor. So factoring out a 3, that gave me x squared plus 4x. Now we have something matching, so we can see that the u sub is going to work. So I would have the integral. I'll go ahead and just write it all out so we can all make sure we see the canceling. That's u du over the u prime. Now those cancel. Over 3, the integral of 1 over u is the natural log of the absolute value of u plus c. This other way where we started doing it and just again trying something, you would do something called partial fraction decomposition, which is a BC topic, not an AB topic. So you will not be doing that. Good for you, I guess. But that's how you would do that one in this class. So that's where I'm going to go ahead and stop notes. Like there's still a lot more that I want to do. And a lot of this, again, is us just kind of like talking through